Look at a glass of water, and the familiar answer feels simple. Earth has oceans because something brought water here. But where did that water actually begin? The old picture points to comets. A stronger picture points to asteroids and water-bearing rock. A deeper picture asks whether some of the chemistry was already present before Earth, before planets, and maybe before the Sun itself. So this is not one delivery story, it is an evidence trail. For the next 2 hours, we are going to follow that trail backward, from oceans to meteorites to isotope clues to young planet-forming disks, and finally to ice hidden on dust inside star-forming clouds. By the end of this video, you will understand why Earth's water probably has more than one source, and why the answer changes what we mean by a habitable planet. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Now we can place the next piece. Begin with the ocean we can see, not as scenery, but as a clue sitting in plain sight. Earth carries more than 1 billion cubic kilometers of water on its surface, and even more may be locked below in minerals, pores, and the deep mantle. From our late vantage point, the blue planet looks inevitable, a rocky world at the right distance from the sun, warm enough for liquid water, cool enough not to boil it all away, familiar enough that we forget how strange the outcome is, but we need the next constraint. A young Earth was not a finished bowl waiting to be filled. It was a construction site made of impacts. Dust stuck to dust. Pebbles became larger bodies smashed into one another. Energy turned into heat. Heat melted rock. Across stretches of early time, parts of the planet may have looked less like land and more like a glowing ocean of magma. Water entering that world did not simply become a sea. It had to survive chemistry, burial, escape, and repeated violence. So we keep the scale in view. Here is why the origin question cannot begin with the word source alone. Source is only one part of the problem. Delivery is another. Retention is another again. A molecule can form in one environment, ride inside a grain or rock through another, be released by impact, dissolve into magma, move through the mantle, escape into the atmosphere, and finally return to the surface much later. By the time we call it ocean water, the original story has been filtered again and again. Think about what happens during giant impacts. Rock vaporizes, atmospheres can be stripped, volatile molecules can be driven upward and lost to space. Other water can be swallowed into molten rock hidden below the surface, or stored in minerals that do not look wet at all. A planet can receive water and still fail to keep it. A planet can begin with hydrogen-bearing ingredients and still lose the final ocean. The blue surface tells us two things at once. Water arrived, and the planet survived long enough to keep it, and we can see why that matters. Early Earth also sat in the warmer inner solar system, close to the young sun. Easy ice was not expected to linger on exposed material the way it could farther out. That old temperature map gave scientists a simple mental picture: dry inner worlds, icy outer bodies, and later delivery across the boundary. The picture helped, it still helps, but the more closely we examine meteorites, isotope ratios, disks, and interstellar ice, the more that clean map starts to blur. Water has many hiding places. It can sit as ice on dust. It can become part of hydrated minerals. It can appear as vapor in hot gas. It can be split apart and later remade. It can move into mantle minerals where no ocean is visible. So when we ask where Earth's water begins, we are not asking where a neat blue drop first appeared. We are asking where the chain first becomes scientifically traceable. A useful way to hold the whole story is to separate three questions. Where did the water molecules or hydrogen-bearing ingredients first form? How did water-bearing material reach the growing Earth? And how did Earth keep enough of it to become an ocean world? Those questions overlap, but they are not the same. Confusing them is how simple origin stories become too confident. The ocean does not answer those questions by itself. It tells us the result. It does not attach a tag saying asteroid, comet, inner disk, molecular cloud, or mantle exchange. For that, scientists need older messengers, fragments that formed when the solar system was young, icy bodies that preserve distant chemistry, ratios inside water that remember temperature and environment, observations of young stars that show how water moves before planets are finished. So the first step is not to leave Earth behind completely. The first step is to make Earth difficult again. A blue planet is not a default setting, it's the outcome of a long argument between supply and loss. Once we feel that problem, the familiar delivery story starts to make sense. If a hot young planet struggles to keep easy water, then small bodies carrying water-bearing material become very important. And that is where the trail moves next, not to a solved answer, but to the leftover rocks of planet formation. Dark fragments, hydrated minerals, ancient bodies that may have carried water through the early solar system and delivered it to a planet still deciding what it could keep. A shoreline hides the violence that made it possible. Every wave depends on a planet massive enough to hold an atmosphere, cool enough to condense water, and geologically active enough to move volatiles between interior and surface. The calm surface is the last page, not the first. Early impacts did not only add material, they also removed material, heated material, and forced water into new chemical homes. A water-bearing body striking Earth could feed the planet and wound it in the same event. Delivery and loss were often tangled together. Magma changes the meaning of wet. Water can dissolve into molten silicate rather than sit above it. Later, when the rock cools and gases escape, that buried inventory can help build an atmosphere or return to the surface. An ocean may partly emerge from what the planet swallowed. Atmosphere matters as much as source. Without enough gravity, gas escapes. With too much early heating, vapor can be stripped away. With the wrong radiation environment, water can split and hydrogen can disappear into space. A source is useless if the planet cannot keep the gift. Earth was balanced near several thresholds, a little smaller, a little hotter, or a little more exposed. And the retained water could have been very different. The planet received material, then had to pass a retention test. That test is why the question stays alive. The word ocean compresses too much history. It hides vapor, ice, hydrated minerals, mantle storage, impacts, escape, and cycling behind one blue image. The visible sea is a summary of invisible processes. Good origin science has to unpack the summary. Water also moves between reservoirs after arrival. Rain falls, rock weathers, seafloor subducts. Magma releases gases, and deep minerals store hydrogen. Over billions of years, surface water and interior water keep exchanging material. The ocean is dynamic, not a sealed container. A source label would be comforting. Asteroid, comet, cloud, mantle. Each word sounds like an answer. But Earth's water passed through too many filters for one label to carry the whole burden. The better answer has to be layered. Starting from Earth keeps the story honest. If we began with interstellar ice, the evidence could accidentally imply that finding old ice solves the planet. Beginning with the ocean problem reminds us that survival is part of origin. Blue is an outcome. The first scientific move is humility. The sea gives us a question, not a receipt. To read the older record, we have to turn away from the water itself and toward the bodies that preserved earlier chemistry. The rocks become witnesses. Water on Earth also has to be counted in more than one place. The sea is visible, but hydrogen in mantle minerals and water in the crust belong to the broader inventory. A source model that accounts only for surface water may miss part of the planet's history. The ocean is the face, not the whole body. The moon-forming impact shows why retention is so difficult. A collision large enough to reshape Earth could heat the planet globally and change its atmosphere. Any water present before such an event had to survive extraordinary conditions or be replaced later. That event keeps the source question open. Cooling matters after violence. Vapor must condense, crust must form, and atmosphere must stabilize before a lasting ocean can sit on the surface. The same water inventory can look very different depending on planetary timing. A planet needs a window for water to settle. The Sun was not a passive background. Young stars can produce stronger radiation and particle activity than mature stars. That environment can erode atmospheres and alter surface chemistry, especially early on. Water lives under a star's pressure. Gravity gives Earth an advantage. A larger planet can hold gases more effectively than a small one, but mass alone is not enough. Temperature, chemistry, impacts, and magnetic environment all matter. Retention is a system property. Early water may have cycled below sight. Even before stable oceans were obvious, hydrogen-bearing material could move into rock, react with minerals, and later emerge through volcanic gases. Invisible water can prepare visible water. The ocean problem also protects against romantic shortcuts. A beautiful cloud map or comet image can make water seem destined for Earth. The young planet reminds us that destiny had to survive physics. Wonder needs friction. Every later chapter returns to this filter. Asteroids, comets, disks, and molecular clouds are all upstream. Earth decides what portion of their contribution remains as an ocean. The endpoint keeps judging the beginning. The first trap is hindsight. Because Earth is blue now, the mind quietly assumes water was always meant to stay. Early planetary physics says otherwise. A rocky world can receive water repeatedly and still end up dry if heat, radiation, or impacts win the contest. The ocean is evidence of a narrow victory. Another trap is treating water as only surface liquid. Planetary scientists have to count hidden forms, hydroxyl in minerals, dissolved volatiles in magma, vapor in atmospheres, ice in small bodies, and hydrogen that can later become water. Once those forms are included, the origin question becomes broader and more subtle. A sea is only one expression of the inventory. The survival frame also explains why Earth is compared with neighbors. Venus, Mars, and the Moon show that inner solar system bodies did not share one simple water fate. Similar regions can produce radically different outcomes when mass, atmosphere, impacts, and geology diverge. Context makes Earth less inevitable, so the ocean problem is not a preface, it's the controlling rule for the whole documentary. Every proposed beginning has to pass through Earth's violent middle before it can become the water we know. The endpoint disciplines every origin claim, or a useful origin story has to survive scale. The same water question spans atoms, rocks, atmospheres, oceans, and galaxies. If any level is skipped, the answer becomes too neat. Earth forces the scales to meet. Here is why we start with the sea and immediately make it difficult. The ocean also teaches patience. A viewer may want the source named quickly, but the source means little until the survival problem is understood. The first mystery is not that water exists somewhere in space. The first mystery is that Earth kept enough of it here. Everything else follows from that. Now we can place the next piece. The classic delivery story deserves respect. It became popular because it solves a real problem. If the inner solar system was too warm for exposed ice to survive easily, and if early Earth was repeatedly melted and battered, then water-rich material from elsewhere offers a natural route. Asteroids, planetesimals, and perhaps comets could bring water-bearing ingredients after the planet had already grown through some of its harshest stages. But we need the next constraint. The most important bodies in this story are not the glamorous ones. They are not bright comets with glowing tails. They are dark, primitive meteorites called carbonaceous chondrites. In ordinary language, they are pieces of ancient solar system material, altered by water long ago. Their minerals carry evidence that liquid water once moved through their parent bodies. They are small, broken records of chemistry from the time when planets were still assembling. So we keep the scale in view. Carbonaceous chondrites matter because their water-related chemistry often looks relevant to Earth. Not identical in every respect. Not a perfect recipe, but close enough to make asteroid-like material one of the strongest source families in the debate. These meteorites show that water was not only floating as ice beyond Earth, it entered rock, it changed minerals, it became part of the solid building blocks that impacts could later deliver. And we can see why that matters. Delivery, though, was never gentle. No soft rain of clean water fell from space onto a finished world. A water-bearing planetesimal arriving at Earth brought rock, metal, minerals, heat, shock, and chemistry. Some of its water could escape, some could react, some could be buried, some could join an atmosphere and later condense. The delivery event was a violent transfer of material, not a simple pour from a cosmic bottle. Here's where we slow down. Late delivery also does not have to mean one final episode at the end. Water-bearing material could arrive across phases of accretion. Some could come before core formation was complete, some could be added during late accretion, some could cycle through the mantle and surface after the early atmosphere changed. The public version often imagines one dramatic arrival. The scientific version is more like a sequence of additions and losses. Look at what we have learned. Asteroid-like delivery remains powerful because it connects directly to things we can hold and measure. Meteorites land on Earth. Laboratories can examine their minerals, hydrogen, oxygen, and isotope ratios. Models can ask how much such material would be needed to account for Earth's inventory. The evidence does not require a single miraculous impact. It asks whether a population of water-bearing bodies could contribute enough over time. But a delivered object has its own history. A carbonaceous body did not create all of its water at the moment it struck Earth. It formed in a young solar system where ice, dust, heat, and chemistry were already arranged by distance from the Sun. If its minerals were altered by water, that water had to be present inside the parent body earlier. And if that water was present there, we have to ask how it got into that body in the first place. Here is the first quiet turn in the story. Delivery can explain how water reached Earth without explaining where the water began. The courier is not the birthplace. An asteroid can carry a message written before the asteroid itself became a fragment. When we study the delivery body, we are also studying the environment that loaded it with water-bearing material. Comets complicate the picture in a different way. They look like the obvious answer because they are visibly icy. They spend much of their lives in the colder outskirts of the solar system. When they approach the Sun, their ice turns to gas and dust, making tails that seem to advertise water from space. For a viewer, the intuition is strong. Earth has oceans, comets have ice. Maybe comets filled the seas. The evidence is not that simple. Many measured comets have water whose heavy hydrogen ratio differs from Earth's oceans. Some comet families come closer than others, so comets are not erased, but the old image of comets as the dominant one-step answer has weakened. Asteroid-like material, hydrated planetesimals, and inner solar system building blocks now carry more of the weight. So the delivery story does two things at once. It gives Earth a plausible way to receive water-bearing material after violent formation, and it pushes the real beginning backward. If asteroids and comets delivered water, they were not the start of the chain. They were vehicles moving older chemistry through a young planetary system. The next clue is hidden inside the water itself, not in the amount of water, but in the kind of hydrogen it carries. A tiny difference in atomic weight became one of the most famous tools in the origin debate. Useful, powerful, and easy to overstate. Carbonaceous chondrites are quiet evidence. They look like dark stones, but inside them are minerals altered by water when their parent bodies were young. That alteration means water was active inside small bodies before those bodies became meteorites. A dry-looking rock can carry a wet history. Hydrated minerals matter because they are durable. Ice can vanish, vapor can escape, and liquid can move away. A mineral changed by water can preserve the encounter long after the original fluid is gone. The evidence survives as structure and chemistry. Delivery through rock is different from delivery through ice. A rocky body can bring hydrogen, hydroxyl-bearing minerals, salts, clays, and trapped water-related compounds. Impact processing then decides what gets released or retained. Earth may have received water in disguised forms. Late accretion gives the model room to work. After major differentiation, additional bodies could still add volatiles to the mantle and surface. The timing matters because early Earth was losing material while still growing. Some water may have arrived after the worst losses. No single meteorite group can carry the whole planet. Samples are partial. Parent bodies vary. The meteorites found on Earth are the survivors of collisions, orbits, atmospheric entry, and collection bias. Strong evidence still needs careful scaling. The asteroid story also explains why water and rock are linked. Earth's oceans are liquid, but much of the origin evidence comes from solids. Not a contradiction. Solids are what survive long enough to be measured. The rock remembers what the water changed. Comets remain emotionally persuasive. They visibly shed vapor and dust when sunlight warms them, so they look like cosmic water carriers. The image is powerful, but imagery is not source accounting. The measurements have to outrank the picture. Asteroid delivery does not make the answer simple. A planet sesamal carrying hydrated minerals inherited those minerals from an earlier environment. Its water history began before its final collision with Earth. The courier has a birthplace too. Delivery can add and erase at once. A high-energy impact may contribute volatiles while ejecting atmosphere or heating the surface enough to drive gases away. Counting incoming water is not the same as counting retained water. Impact arithmetic is not simple addition. The delivery model earns its place by solving a real gap. A hot inner planet needs help explaining its final inventory. Water-bearing small bodies provide that help, but they also open the door to a deeper origin story. Delivered water still has an ancestry. Carbonaceous parent bodies were not uniform worlds. Some heated enough for water to move through their interiors, some preserved colder material. Some were shattered and reassembled. That variety helps explain why meteorite evidence is rich but not perfectly clean. The mess is part of the record. Hydrated rock can survive where exposed ice cannot. Closer to the sun, pure ice may be unstable, yet water bound in minerals can persist longer. That makes rocky carriers especially important for an inner planet. Water can travel undercover. Dynamical pathways are required. A water-rich body does not help Earth unless its orbit changes. Gravitational interactions, planetary migration, and scattering can move bodies across the early solar system. Chemistry needs celestial mechanics. The asteroid belt is a remnant, not a full archive. The bodies we see today are survivors of billions of years of collisions and orbital sculpting. Early populations may have been larger and differently arranged. The delivery inventory has partly vanished. Late veneer ideas add another layer. Material arriving after core formation may explain certain chemical signatures and volatile additions, but the timing and composition remain debated. Late does not mean simple. Water-bearing impacts would have affected atmosphere. Released vapor could thicken the atmosphere, rain out later, or escape depending on energy and conditions. Delivery connects directly to climate and retention. The impact and the air were linked. Asteroids preserve process in physical form. They tell us that solids could incorporate water, alter internally, and survive long enough to move through the system. The delivery story is also a storage story. Once storage is admitted, origin moves earlier. A body that stored water had to acquire it during formation or alteration. That pushes us back to disk temperature, ice lines, and inherited chemistry. The rock points behind itself. Asteroid delivery also fits the practical evidence trail. Meteorites give laboratories actual material rather than distant light alone. Scientists can heat them, dissolve them, measure isotopes, examine minerals, and compare them with terrestrial rocks. That directness gives asteroid-like sources unusual strength in a field full of inference. The strongest clue may be the one that fell to Earth. The parent bodies themselves were small worlds. Some had enough internal heat for liquid water to move through rock, forming clays and other hydrated minerals. They were not planets, but they hosted chemistry that prepared water-bearing material for later delivery. Before they struck Earth, they had histories of their own. A delivery model must also match timing. Water added too early could be lost during later giant impacts. Water added too late must still explain mantle reservoirs and isotope relationships. The window is not a single moment, but a sequence of opportunities and hazards. Timing decides how much delivery counts. By the end of the delivery chapter, the answer has already deepened. Asteroids may explain a major part of how water arrived, but they cannot be the ultimate beginning if their own water was inherited from disk chemistry. The road continues behind the messenger. Water-bearing bodies carry more than cargo. They are evidence of a young solar system where rock and water interacted before Earth's surface stabilized. Their minerals preserve environments that no longer exist in their original form. Delivery becomes a way of reading lost worlds. The strongest delivery argument still leaves one question untouched. If hydrated bodies supplied Earth, then the water in those bodies had already been incorporated, altered, or preserved earlier. The delivery story explains arrival better than birth, so the trail keeps moving backward. Now we can place the next piece. Water carries hydrogen. Most hydrogen is simple. One proton, one electron, and almost no mass compared with larger atoms. But a small fraction of hydrogen has an extra neutron. That heavier form is called deuterium. When scientists compare deuterium to ordinary hydrogen in water, they get a ratio, and that ratio can act like a clue to the conditions where the water formed or changed. What this changes is the picture of water as a simple substance. Even a familiar ocean carries a memory of temperature, chemistry, and loss. But we need the next constraint. The phrase often used is fingerprint. It's tempting because it feels decisive. Fingerprints identify one person. A deuterium to hydrogen ratio seems as if it should identify one source. But water is older and messier than a fingerprint at a crime scene. Ratios can be changed by temperature, chemistry, evaporation, atmospheric escape, parent body alteration, and mixing between reservoirs. The clue is real, the barcode metaphor is too strong, so we keep the scale in view. Still, the clue changed the debate. If Earth's ocean water has one DH ratio and a comet has a very different ratio, then that comet cannot simply stand in for the whole ocean. Many measured comets, especially from long-period or Oort cloud populations, are enriched in deuterium compared with Earth. That mismatch made a comet-dominated origin harder to defend in its simplest form, and we can see why that matters. Some Jupiter family comets are closer to Earth's ratio, and that matters. The comet story did not vanish. A diverse comet population may include bodies whose water resembles terrestrial water more closely than others. Sampling is limited, objects vary, measurements are difficult. The honest conclusion is not that comets never contributed. The honest conclusion is that comets are unlikely to be the easy universal answer viewers once imagined. Here's where we slow down. Carbonaceous chondrites often fit the terrestrial water story better. Their hydrated minerals and isotope values make asteroid-like bodies attractive contributors. They are not pure ice. They are rock that interacted with water, which may actually be closer to the way Earth received much of its inventory, not as clean frozen chunks, but as water-bearing minerals, hydrogen-rich material, and altered small bodies folded into planetary growth. Look at what we have learned. DH also links our solar system to older environments. Cold chemistry tends to enrich molecules in deuterium. In molecular clouds and early star-forming regions, low temperatures can leave distinctive heavy hydrogen signatures. If similar enrichments appear across protostars, disks, and comet-like bodies, scientists can ask whether some water chemistry passed through multiple stages instead of being completely destroyed and rebuilt every time. That possibility is exciting because it connects scale. A ratio in a meteorite or comet can point beyond the small body itself. It can hint at the disk. The disk can hint at the protostar. The protostar can point back to the molecular cloud. A tiny atomic difference becomes a thread running through environments too large and too ancient to watch directly, but the thread can fray. Parent bodies warm, ice melts, water alters minerals, radiation changes molecules. Atmospheres lose lighter hydrogen more easily than heavier hydrogen. Sampling one comet, one meteorite group, or one reservoir can mislead if we treat it as the entire story. The ratio narrows suspects. It does not draw a clean line from cloud to ocean. That restraint is important for the viewer promise. We are not replacing one oversimplification with another. Comets did it was too simple. Asteroids did it can also become too simple. Interstellar ice did it would be even more dangerous if said without the delivery and survival filters. The Isotope Clue teaches the opposite lesson. Origins are reconstructed by overlapping constraints, not by one magic number. So when we follow D-Pratch backward, we do not arrive at a single source label. We arrive at a deeper question. What kind of material built Earth? Was it completely dry at first, waiting for outer solar system water to arrive? Or did some of the ingredients that formed Earth already carry meaningful hydrogen, hidden in minerals that older models underestimated? That question moves the story inward, away from bright comet tails, away from the image of icy bodies alone, into meteorites that look dry at first glance, yet may contain enough hydrogen to challenge the old map of a dry inner solar system. Deuterium turns water into a historical clue. Because heavy hydrogen behaves slightly differently in chemical reactions, cold environments and later processing can leave measurable patterns. Those patterns are small, but they are not random. A tiny atomic difference can carry cosmic memory. The fingerprint metaphor helps at first. It tells us that not all water reservoirs look chemically identical. Oceans, comets, meteorites, protostars, and disks can be compared by ratios rather than by appearance. A number can challenge a beautiful image. The metaphor fails when treated too literally. A human fingerprint points to one person. A D-arch ratio reflects formation, mixing, alteration, and loss. Several histories can converge towards similar numbers, and one reservoir can change through time. The clue is powerful because it is limited. Comet measurements forced a correction. Icy bodies seemed obvious until many measured ratios came out too high compared with Earth's ocean water. The mismatch weakened the old one-step comet story. Ice alone was not enough. Jupiter family comets keep nuance alive. Some have ratios closer to terrestrial water, which means the comet category is diverse. A careful answer leaves room for contribution without handing comets the whole ocean. Nuance prevents overcorrection. Meteorites often look more promising. Carbonaceous chondrite water-related chemistry can sit nearer to terrestrial values, making asteroid-like sources more compelling in many models. The fit is not perfect, but it is serious. The duller objects became stronger suspects. Atmospheric escape can alter Earth's own ratio. Lighter hydrogen can be lost more readily than deuterium under some conditions. That means the present ocean ratio may not be a pristine snapshot of the first inventory. Even the target has history. Parent body processing alters the source side. A small body can warm internally, melt ice, form hydrated minerals, and exchange hydrogen between reservoirs. By the time we sample it, its water has already been through a story. The suspect has changed clothes. The isotope clue is strongest in combination. Matched with mineralogy, dynamics, disk observations, and models, DH becomes part of a web. Alone it can mislead. Together it narrows the honest answer. No single number should carry the ocean. The ratio ultimately points backward. If comet and meteorite water carry chemical memories, then the source bodies inherited conditions from the disk and perhaps from the cloud before the disk. A fingerprint becomes a trail. O Hadl, DH became famous because it is measurable. Scientists can compare ocean water, meteorites, cometary vapor, and distant reservoirs using a shared chemical language. That common measure lets very different objects enter the same debate. One ratio connects many worlds. Heavy hydrogen is sensitive to cold. Low-temperature chemistry can enrich deuterium in certain molecules, which is why the ratio can preserve hints of molecular cloud or outer disk conditions. Cold leaves a signature. Earth's ocean value is not a perfect original. The present ratio reflects the planet after atmospheric escape, geological cycling, and possible mixing between sources. It's the target, but the target has evolved. Even home is processed. Comet diversity matters for sampling. A few measured objects cannot represent every icy body that ever existed. Some families may have contributed more plausibly than others. The population is wider than the sample. Meteorite water is measured in minerals. Scientists often infer water history from hydrated phases and hydrogen-bearing compounds, rather than liquid water trapped like a droplet. The evidence is mineral memory. Fractionation can happen in many settings: evaporation, condensation, reactions on grains, alteration inside parent bodies, and escape from atmospheres can all shift ratios. Many processes can write on the same page. Here is why models are necessary. A measured ratio becomes meaningful only when paired with physical histories that could produce it. Numbers need pathways. Chemistry and dynamics work together. The biggest mistake is certainty too early. DH can exclude simple versions of a source story, but it rarely crowns one source alone. It narrows the path rather than ending the walk. The clue keeps us moving. Ratios are seductive because they feel objective. A number seems cleaner than a story, but the number only becomes an origin clue when scientists understand the processes that changed it. Without that context, precision can create false certainty. Measurement is not interpretation by itself. Earth's standard ocean value became the comparison target. Every proposed source is partly judged against it, yet the ocean value is the product of Earth's history, not a pristine sample from day one. That makes the comparison useful and imperfect at the same time. The benchmark has been processed. The comet correction was one of the great public surprises. Objects that looked most watery did not always look chemically right. That mismatch is exactly why science needs measurements that can overturn intuition. The obvious source lost its monopoly. DH leaves us with a disciplined question. Which reservoirs can match Earth closely enough, arrive in the right amounts, and survive the planetary filters? Only when all three conditions are considered does the ratio become meaningful. The clue needs the chain. A ratio can also reveal false simplicity. When comet values differ from oceans, the mismatch does not solve the case by itself, but it prevents a lazy answer from surviving. Good evidence often works first by removing bad certainty. The path narrows, so DH gives the evidence trail its method. Compare reservoirs, test the match, ask what could have changed the number, and refuse to treat similarity as proof without a root. That method will matter again in disks and clouds. The clue teaches discipline. Now we can place the next piece. For a long time, the simple mental map was useful. The inner solar system was hot and dry. The outer solar system was cold and wet. Rocky planets formed inside, icy bodies formed outside, and water came inward later. The map is clean enough to teach quickly. It explains why asteroids and comets became so important. But nature rarely keeps the borders as sharp as our diagrams. What this changes is the picture of early Earth as an empty, dry rock. The ingredients under our feet may have mattered before any late delivery arrived, but we need the next constraint. Enstatite chondrites sit right at that uncomfortable border. They are meteorites with chemical and isotopic similarities to Earth-building material. They formed in the inner solar system under conditions once treated as too dry to matter much for water. Yet work on these meteorites, including the 2020 science study led by Lauret Piani and colleagues, suggested that such material could contain enough hydrogen to contribute meaningfully to Earth's water inventory if scaled through planet formation, so we keep the scale in view. Careful wording matters here. The claim is not that enstatite chondrites themselves were little oceans. They are meteorites, not miniature Earths. The claim is not that they solve the whole ocean. The stronger and safer point is more interesting. Materials similar to Earth's building blocks may not have been as water-poor as the old, dry, inner Earth story assumed, and we can see why that matters. Hydrogen is the key. Water does not always appear in the form our eyes expect. It can be bound in minerals, or present in chemical forms that later become water during planetary processing. If Earth accreted from material carrying enough hydrogen, then some portion of its water-related inventory may have been present from the start, or at least from very early assembly, rather than arriving only as a late outer solar system gift. Here's where we slow down. That changes the emotional shape of the story. Earth may not have been a bone-dry rock waiting helplessly for asteroids to rescue it. It may have grown from ingredients that already contained part of the answer. Delivery still matters. Carbonaceous bodies still matter. Late accretion still matters. But the starting condition becomes less empty. Look at what we have learned. The old boundary between local and delivered water starts to soften. Some water-related inventory could be local in the sense that it arrived with Earth-forming material. Some could be delivered by asteroid-like bodies from farther out. Some could be linked to even older ice chemistry inherited into the disk. The point is not to make every source equal. The point is to stop forcing the evidence into a single lane. Imagine we are following the evidence. Meteorites also remind us how indirect this work is. No meteorite is a perfect sample of bulk Earth. Each one comes with parent body history, alteration, shock, heating, and selection bias. The fragments that reach our laboratories are survivors. They tell the truth, but not the whole truth. Scientists have to compare them with models, isotope systems, and other samples before turning them into a planetary origin story. That uncertainty does not weaken the evidence, it gives it force. If even the supposedly dry inner material may have carried more hydrogen than expected, then the question, where did Earth's water come from, cannot be answered only by looking outward. The ingredients of Earth itself become part of the evidence trail. Now the scale has shifted again. We began at the ocean. We moved to impacts and meteorites. We looked at atomic ratios. Then inner solar system rocks complicated the old dry versus wet map. The next step is to ask where all of those building blocks formed before there were planets at all. Before Earth had oceans, before asteroids struck its surface, before meteorites became samples in laboratories. The young sun was surrounded by a disk of gas and dust. Inside that disk, water could freeze, vaporize, react, migrate, and become trapped in the raw material of future worlds. The dry inner solar system was a useful simplification. Close to the young sun, high temperatures made exposed ice difficult. That made the inner planets seem naturally water-poor and the outer solar system naturally water-rich. Useful maps are not always final maps. Enstatite chondrites made the map less tidy. Their Earth-like isotopic relationships make them relevant analogues for the material that helped build our planet. Finding meaningful hydrogen in such material changes the starting picture. Dry ingredients may not have been completely dry. Hydrogen can become water later. A material does not need to contain liquid water to matter for an ocean. Hydrogen bound in minerals or compounds can participate in reactions during planetary growth. Water inventory can begin as chemistry, not liquid. Scaling remains the hard part. Meteorite measurements must be translated into planetary masses, formation pathways, and losses. A sample can show possibility without proving exact contribution. The claim is significant but bounded. Local inventory changes the delivery debate. If Earth-forming material carried some water-related ingredients, then outer delivery was adding to a non-zero baseline. The planet may have started with part of the story already inside. The empty bowl image begins to crack. Inner material does not erase asteroids. Carbonaceous bodies still offer strong evidence for later or additional water-bearing contributions. The point is mixture, not replacement. One clue can grow without shrinking every other clue. The finding also affects timing. Water-related ingredients present during accretion would experience core formation magma oceans, and early differentiation. Late delivered water would enter a planet already partly organized. When water arrives, changes what happens to it. A local contribution would still have older ancestry. The material that formed close to the Sun came from the solar nebula, which came from a collapsing cloud. Local does not mean newly invented from nothing. Even local water can have deep roots. The lesson is restraint. Earth may not have been born bone dry, but that does not give us a full ocean recipe. It gives us a wider set of ingredients to test. The old binary becomes a spectrum. Once the building blocks matter, the disk matters. To understand what Earth inherited locally or received from farther out, we have to examine the young environment where those solids grew. The story moves from rocks to the factory. The word dry can mislead. In planetary science, dry may mean poor in volatiles compared with icy bodies, not absolutely empty of hydrogen. A small fraction scaled to Earth mass can become significant. Tiny percentages can matter at planetary size. Enstatite material sits close to Earth chemically. That connection makes it more relevant than a random meteorite group when asking what the inner planet inherited. Similarity gives the sample weight. The finding also changes public intuition. Viewers often imagine water as something that had to come from obviously icy places. Hydrogen-bearing inner rock breaks that visual shortcut. The wet clue may not look wet. Core formation complicates inventory. As metal separated from silicate, volatile elements could partition, escape, or remain in the mantle. Early water-related material had to pass through differentiation. Being early was not automatically safe. Local and delivered sources can interact. A planet with some initial hydrogen can later receive hydrated material, mixing reservoirs until the final ocean no longer remembers a single clean origin. Mixture begins early. Meteorite analogues require caution. No scientist can simply grind an enstatite chondrite and call it Earth. The power lies in showing plausible ingredients, not exact replication. Analog is not duplicate. The inner solar system was chemically diverse. Temperature mattered, but so did pressure, oxidation state, local mixing, and timing. One zone could contain more variety than a simple diagram suggests. The map gains texture, so the dry Earth chapter opens the door inward. Earth's water may be partly inherited through its own building material, not only imported from distant ice. The source question turns inside out. The Isotope Clue is easy to understate because it lacks visual drama. No glowing comet, no blue ocean, no spectacular telescope image, just careful measurements inside meteorites. Yet, those measurements can change the assumed starting inventory of Earth. Quiet evidence can move the whole frame. If hydrogen was present early, it faced harsher processing. Early inventory would pass through accretion, melting, differentiation, and possibly the moon-forming impact. Later inventory might avoid some of that. Different arrival times create different survival odds. Early is not automatically better, and the dry Earth story becomes a layered story. Earth may have started with some ingredients, received others, lost some, stored some, and later recycled some. The final ocean could represent several phases rather than one decisive episode. The answer becomes geological as well as astronomical. This point also prevents an outer space-only bias. Water origin is not only about what came from far away. Some of the answer may sit in the ordinary-looking material that built the inner planet itself. The source may be partly under our feet. The old dry model was not foolish. It came from real temperature logic and real expectations about the inner solar system. The revision matters because science improved the evidence, not because the old map was careless. Better samples made a sharper question. Inner hydrogen also changes the emotional answer. Earth may have carried part of its future ocean inside unpromising material from the beginning. The story becomes less like rescue from outside and more like assembly from mixed ingredients. The planet was not simply waiting. Picture the solar system before the solar system was finished. No Earth, no Mars with a rusty surface, no asteroid belt as we know it. A young sun sits at the center, wrapped in a disk of gas, dust, ice, and growing solids. The disk is not empty background. It's the factory floor where planet ingredients are sorted, heated, frozen, moved, broken, and rebuilt. Now we can place the next piece. Temperature gives the disk structure. Close to the star, water tends to exist as vapor if it survives at all. Farther out, where conditions are colder, water can freeze onto grains. Between those regimes sits the snow line, a boundary that is less like a painted circle and more like a changing weather front inside the disk. Cross it, and the same molecule can behave differently. But we need the next constraint. The snow line matters because solid ice changes how material grows. Icy grains can stick differently from dry grains. Pebbles carrying ice can drift inward. Bodies forming beyond the snow line can become water-rich compared with those forming closer in. Later, gravitational stirring and migration can scatter that material into regions where rocky planets assemble. Delivery starts to look less like an accident and more like a consequence of disk architecture, so we keep the scale in view. The disk also decides what gets reset. Heat can break old molecules apart or drive water out of solids. Cold regions can preserve ice. Radiation can alter chemistry at exposed surfaces. Turbulence and radial drift can mix material from one region into another. A molecule born before the star may be destroyed. Another may survive. A third may be broken and remade while keeping an isotope clue that still points to cold chemistry. And we can see why that matters. Here is why disk science sits at the center of the origin question. If all water were completely reset during star and disk formation, then interstellar ice would be a distant ancestor with little direct relevance to Earth. If some water or some chemical signature survives into the disk, then the beginning of the trail can move back before planets. The difference changes how we think about every ocean world. Here's where we slow down. Young disks are difficult to observe. They are far away, full of dust, and much of their water is hidden as ice. Telescopes often see indirect signatures or specific regions rather than a complete inventory. Even so, the disk stage gives scientists something Earth cannot: a chance to watch planet-making material before planets erase the record. It shows water not as a late decoration, but as part of the construction environment. Look at what we have learned. For rocky planets, location is destiny only in part. A planet forming near the star may begin in a relatively dry zone, but its building blocks can include material that moved. Pebbles drift, planetesimals scatter, embryos collide. Giant planets, if present, reshape the flow. The path from disk to planet is dynamic, which means water can cross boundaries that a simple textbook diagram makes look fixed. Imagine we are following the evidence. DH returns here as a bridge. If water in a disk has a ratio that resembles water in comets and earlier protostellar material, scientists can ask whether the disk inherited part of its water, rather than manufacturing everything from scratch. Not a final answer for Earth, but it is a direct challenge to the idea that the water story starts only when asteroids hit a finished planet. The disk also reframes asteroids and comets. They are not independent sources floating outside the history. They are products of the disk. Their water content, minerals, isotope ratios, and eventual delivery paths all depend on conditions before they became the objects we name. To understand a delivery body, we have to understand the disk that loaded it with water-bearing material. A rare young system made that problem much easier to see, not because it was our solar system, not because it solved Earth, because it exposed water in a planet-forming disk in a way that connected several stages of the chain. The name is V883 Orionis, and its value comes from a temporary act of illumination. A protoplanetary disk is organized by heat. Near the star, water can be vapor. Farther out, it can freeze. Between those regions, conditions shift over time as the star brightens and the disk evolves. Water changes address as the disk changes temperature. The snow line is a moving boundary. It's often drawn as a neat ring, but real disks evolve. outbursts, accretion rates, dust opacity, and time can move the zone where water freezes. A boundary in a young system is not a wall. Fireballs make water mobile. Small icy solids can drift inward through gas drag. As they cross warmer regions, ice can vaporize, enrich gas, or refreeze elsewhere. The disk can transport water before planets exist. Planetesimals lock chemistry into larger bodies. Once grains and pebbles grow, water can become protected inside rock and ice. That protection lets material survive long enough to be scattered or delivered. Small bodies become storage devices. Disk chemistry can preserve and remake at once. Some molecules survive cold paths. Others are destroyed and reassembled. Isotope signatures may be partly inherited, partly reset, and partly mixed. Continuity comes in fractions. Young disks are not easy laboratories. They are distant, dusty, and structured. Observations often capture vapor, warm surfaces, or exceptional cases rather than the full water budget. Every telescope view has a selection effect. Still, disks answer a key question. They show that water belongs to the planet-forming environment itself. Before finished worlds exist, water is already being sorted into reservoirs. The ocean story has a pre-planetary chapter. Disk dynamics blur source categories. Material born beyond the snowline can move inward. Material near the star can mix outward. Growing planets can scatter bodies across regions. Where something formed and where it ended up can differ. The disk links meteorites to clouds. Meteorites preserve solid records, while clouds provide earlier ice chemistry. The disk is the transition where one kind of evidence can become another. Without the disk, the chain breaks. Here is why V883 Ori matters. It gave scientists a rare chance to see water chemistry in a planet-forming disk with enough clarity to compare it with earlier and later reservoirs. A young star became a bridge. Disk gas shapes solid motion. Pebbles feel drag and spiral through the disk, carrying ice or dry minerals across regions. That movement can redistribute water before planets form. The disk is a conveyor belt. Ice changes sticking and growth. Frozen mantles can alter how grains collide and clump, affecting the pace of planet sesamal formation beyond the snowline. Water influences architecture before oceans exist. Vapor can enrich inner regions temporarily. When icy material drifts inward and sublimates, water vapor can increase in warmer zones where it may react or later move outward again. The boundary breathes. Outbursts can rewrite snowlines. Young stars do not always shine steadily. Brightening events can heat disks and reveal or relocate water reservoirs for a time. A disk has weather of its own. Observing ice directly is difficult. Much of the cold water sits hidden in midplanes where dust blocks our view. Scientists often rely on vapor, surface layers, or unusual systems. The easiest water to see is not always the bulk water. The disk stage creates future evidence. Material processed here becomes meteorites, comets, asteroids, and planets. Later samples are downstream records of disk conditions. The factory labels the products imperfectly. Migration can scramble birthplace. A body found in one region may have formed elsewhere or incorporated material from elsewhere. Source categories become dynamic. Location is not identity. Planet formation starts before planets are named. By the time Earth exists, much of the water sorting has already happened in solids too small to see from far away. The origin hides in prehistory. The disk stage is where categories begin to form. Future asteroids, comets, planets, and dust populations are all being sorted from the same evolving material. Later names can make them seem separate, but the early disk ties them together. The family resemblance starts before the family members are finished. A snowline also affects abundance. Beyond it, water ice increases the amount of solid material available for growth. That can shape how quickly larger bodies form and how much water-rich material exists for later scattering. Water changes the construction budget. The disk is also a chemical clock. Short-lived heating events, Gradual cooling and mixing leave time-dependent signatures. A body forming early may preserve a different water history from one forming later. When a pebble grows matters. By moving into the disk, the story stops being only about Earth. We are now asking whether water is a general ingredient of planet formation, and how often that ingredient survives into rocky worlds. Earth becomes one case in a larger experiment. The disk is where water becomes planetary material. Before that, ice belongs to the cloud. After that, water belongs to bodies with orbits, interiors, and collision histories. The disk is the handoff between chemistry and architecture. That handoff is central. Listening to the disk chapter should change the viewer's question. Instead of asking only what hit Earth, we ask what those impactors inherited, where they formed, and how the disk sorted them before they ever crossed Earth's path. Delivery gets a prehistory. Now we can place the next piece. V883 Orionis is a young star system hundreds of light years away. It's not the Sun. Its planets, if they form, are not Earth. But for the water origin question, it gave scientists something rare, a better look at water in a planet-forming disk. Usually, much of the water in disks is frozen and hidden, especially in the colder outer regions where comet-like bodies form. What this changes is the picture of planet formation as a clean reset. A young system may inherit more chemistry than it invents from scratch. But we need the next constraint. V883 Ori went through an outburst. The young star brightened, warming the surrounding disk and pushing the water snow line outward. Water that would normally sit frozen in regions hard to study became vapor over a larger area. That made it easier for observatories such as ALMA to detect and compare the water's chemistry. A temporary brightening turned a hidden reservoir into an observable one. Holes, we keep the scale in view. The 2023 Nature work by John Tobin and colleagues used that opportunity to examine deuterium-enriched water in the disk. The important phrase is not solved. The important phrase is tied. The water chemistry in V883 Ori helped connect planet-forming disks to protostellar water and comet-like reservoirs. It supported the idea that some water can pass through stages of star formation without being completely reset, and we can see why that matters. That finding matters because it gives the inheritance story observational weight. Instead of saying, maybe old cloud water survives, only from models, scientists had a young disk where the ratio could be compared across stages. If disk water resembles earlier protostellar water and later comet-like reservoirs, then the chain from cloud to disk to small icy bodies becomes more than a poetic idea. Here's where we slow down. Still, the boundary is strict. V883 Ori is not Earth's birthplace. It does not tell us how much of Earth's ocean water came from inherited interstellar ice. It does not bypass meteorites, asteroids, comets, or the violent history of the early Earth. It shows that the kind of continuity required by the older-than-the-sun question is scientifically plausible in at least some young systems. Look at what the evidence has added. That distinction is the heart of the question. Plausible inheritance is not a solved genealogy. A chemical tie is not a tracked molecule. But the tie matters because it changes the scale of the question. Earth's water story may not begin when an asteroid crosses Earth's orbit. Part of the story may begin when water chemistry survives the making of a star and enters the disk where planets form. Imagine the sequence slowly. A cold cloud holds dust and ice. Gravity gathers part of that cloud into a collapsing core. A protostar forms at the center. Around it, a disk spreads outward. Some material heats and changes. Some freezes and stays cold. Some moves, some survives. Later, grains become pebbles. Pebbles become planetesimals. And planetesimals become the bodies that strike worlds or remain as comets. No single observation captures all of that. V883 Ori gives one window, not the whole house. But a good window can still change the map. It shows that water in a planet-forming disk can carry a chemical relationship to earlier stages. Once that relationship is visible, the old delivery story starts to look like the last few chapters of a longer book. The phrase "older than the sun" becomes tempting here, and it needs discipline. Some water molecules or some chemical inheritance may predate the star that eventually made Earth. That does not mean the Pacific Ocean sat preserved in a cloud. It does not mean every water molecule in your body is older than the sun. It means part of the chemical ancestry may reach back into the pre-solar environment. So the trail now points beyond the disk. If water chemistry can enter a disk already carrying an older signature, where did that water exist before the star turned on? The answer takes us into the coldest and least visible part of the story. Ice on dust grains inside molecular clouds. V883 Ori became useful because it brightened. The outburst warmed the disk and moved the snowline outward, exposing water vapor that would otherwise be frozen and hidden from easy observation. A temporary flare opened a chemical window. Water vapor can speak through spectral lines. Telescopes do not need to scoop the water. They read light from molecules and compare the signatures with models. Remote chemistry becomes possible when the conditions cooperate. The Tobin result connected stages. The deuterium-enriched water in the disk aligned with the broader idea that disk water, protostellar water, and comet-like reservoirs can share chemical ancestry. The chain gained an observed link. Connected does not mean identical. A ratio can show relationship without proving that every molecule survived unchanged. Some water may have been inherited, some reset, and some remade. The strongest claim is partial continuity. The system is not our own. V883 Ori cannot be used as a direct biography of Earth. Its value lies in showing a process that may operate in planet-forming environments. Analogy is useful when kept honest. Inheritance changes the starting line. If water can pass into disks with older signatures, then asteroids and comets may carry chemistry that began before they existed. Delivery bodies become heirs. The observation also helps explain comets. Comets are thought to preserve cold outer disk material. Similarities between disk water and comet-like reservoirs make their chemistry part of a longer sequence. The icy tail is not the beginning. V883 Ori gives the viewer a real object. Instead of abstract inheritance, we can picture a young star heating its disk and revealing water that normally hides beyond the snowline. The science becomes visible. Bounded wonder is still wonder. Some water ancestry may predate a star, yet the final ocean depends on everything that happens afterward. The phrase "older than the sun" needs that boundary. Precision keeps the ore intact. The next step lies before the disk. If a disk can inherit water chemistry, then the pre-disk reservoir becomes central. That reservoir is not a planet or comet, it's ice on dust in a molecular cloud. The trail enters darkness. The snow line shift made V883 Ori special. Water that normally freezes too close to the midplane became observable farther from the star. That rare geometry gave scientists a clearer chemical sample. Nature briefly moved the curtain. ALMA could read millimeter signatures. Those observations helped measure water isotopologues and compare deuterium enrichment in the disk environment. The clue came through light, not sampling. The result strengthened continuity arguments. Disk water did not appear chemically isolated from earlier protostellar water or later cometary reservoirs. The stages looked connected. The chain gained coherence. Continuity has survival implications. If water chemistry survives into disks elsewhere, then some early molecular cloud inventory may become available to planetesimals. The cloud can reach the construction zone. Earth remains several steps removed. Our planet needs solar system-specific dynamics, meteorite evidence, and retention history before V883 Ori can inform the final answer. A bridge still needs the road on both sides. The observation also disciplines speculation. It supports possible inheritance, but it does not quantify Earth's inherited fraction. That number remains model-dependent. The clue is direction, not inventory. Young star studies expand the comparison set. Each disk observed adds another test of whether water inheritance is common, rare, or dependent on local conditions. One system opens a survey question. For narration, V883 Ori gives the midpoint. It stands between invisible cloud chemistry and familiar solar system bodies, making the backward trail easier to hear. The listener gets a stepping stone. Ori 883 Ori matters because hidden water became exposed. Most disk water sits in places where observation is frustrating. The outburst changed the geometry, making the system a natural experiment rather than a normal snapshot. A rare condition made a rare measurement possible. The comparison to comets is especially important. Comets are thought to preserve cold material from planet-forming disks. If disk water chemistry lines up with comet-like reservoirs, the solar system delivery bodies gain a deeper context. The comet becomes an archive of disk inheritance. Scientists still avoid the strongest possible claim. The result supports a link between stages, not a complete molecule-by-molecule survival story. That caution is what makes the finding useful rather than promotional. A bounded claim can carry more trust. For the viewer, V883 Ori is the hinge. Before it, we have solar system samples and ratios. After it, we can imagine water chemistry moving through young disks from older clouds. The trail bends toward the pre-solar dark. V883 Ori also shows why exceptions are valuable. A normal system may hide the very water scientists most want to measure. An outburst creates unusual conditions that expose the hidden chemistry. The exception becomes a tool. Rare does not mean irrelevant. The young star clue does not close the case. It gives the inheritance idea a real observational anchor, then hands the question onward to colder material still farther back. The best evidence often works like that. One doorway opens another. Now we can place the next piece. A dust grain inside a molecular cloud is almost impossibly small, smaller than a speck, smaller than the motes you see in sunlight. Yet, in the origin story of water, that tiny surface matters. Space is not empty in these clouds, but it is thin. Atoms and molecules drift through darkness, and without surfaces they do not always meet or react efficiently. Dust gives chemistry a place to happen. What this changes is the scale of the question. A shoreline may depend on chemistry that began on grains too small to picture easily, but we need the next constraint. Cold changes everything. In a dense molecular cloud, temperatures can fall so low that atoms and simple molecules stick to grain surfaces. Oxygen can meet hydrogen there. Reactions can build water. The newly formed water freezes, adding to an icy mantle around the grain. Layer by layer, invisible to human eyes, a dust particle becomes coated with frozen chemistry. So we keep the scale in view. One grain is nothing. A whole cloud is enormous. Multiply those thin ice mantles across countless grains, and the result is a hidden reservoir spread through a star-forming environment. No ocean, no lake, no liquid surface, just ice locked to dust, mixed with other frozen molecules, waiting inside the same dark material from which stars and disks may later form. And we can see why that matters. Here is the point where the familiar water story becomes physically strange. The water we know as liquid, reflective, and heavy in the hand may have an ancestry in something nearly weightless. A cold coating on dust, chemistry in darkness, not rain from a sky, but reactions on surfaces no eye could ever see. The beginning, if we can call it that, is not dramatic. It's quiet and microscopic. Here's where we slow down, seeing that ice is difficult. Molecular clouds are dark because dust blocks visible light. The ice itself is cold. It does not shine like a star. Scientists often identify it by the way molecules absorb or emit specific wavelengths of light. Water ice leaves signatures. Other substances do too. The job is to separate those signatures carefully enough to map what is present without turning the map into more certainty than it deserves. Look at what we have learned. Organic molecules and PAHs often appear in the same broader environments. They matter because star-forming clouds are chemically rich, not sterile, but water, ice, and carbon-rich molecules are not interchangeable. A responsible script keeps them separate. Water ice helps trace the reservoir relevant to the water story. PAHs and organics help show the broader chemical richness of the cloud. Imagine we are following the evidence. The dust grain stage also explains why water from space can be a misleading phrase. It sounds like water waits somewhere as floating drops and then falls onto planets. The real story is more granular. Water can be assembled on surfaces, frozen into mantles, carried into collapsing material, processed in disks, trapped in small bodies, and later released through impacts or geological cycling. Space is not the delivery truck, it's the first workshop. Think of the system this way. Interstellar ice does not automatically become Earth's ocean. That has to be said clearly. A cloud reservoir can feed a star-forming region. A fraction of material can enter a disk. Some of that material may preserve older chemistry. Small bodies may incorporate it. Planet formation may destroy, mix, or retain it. The cloud is an early reservoir, not a guaranteed destination. Yet the reservoir matters because it moves the origin question backward to a place before planets. If water forms efficiently on dust in cold clouds, then the story starts before planets. It's part of the raw material out of which solar systems can emerge, and that changes the frame, even with every caution left intact. For a long time, that earliest reservoir was hard to make vivid for viewers. Meteorites can be held, comets can be photographed, oceans can be filmed. Dust grain ice inside a molecular cloud sounds almost imaginary until an instrument maps chemical signatures across a real star-forming region. And that is where SPHEREx enters the story. Dust gives atoms a meeting place. In thin interstellar gas, encounters can be rare. A cold grain surface lets atoms stick long enough for reactions to happen. The smallest stage can control the largest consequence. Water formation on grains is physical chemistry. Oxygen-bearing species and hydrogen atoms interact on surfaces, and the resulting water freezes into mantles under cold conditions. No ocean is needed for water to begin. Ice mantles are thin but numerous. One coated grain is negligible. Countless coated grains across a cloud create a reservoir that can feed future star-forming material. Scale turns dust into supply. Molecular clouds hide their contents. Dust blocks visible light, and cold ice does not shine brightly. Scientists rely on absorption and emission features to infer what is present. The reservoir announces itself indirectly. The darkness is not empty. Alongside water ice, clouds contain carbon monoxide ice, carbon dioxide ice, organics, and complex carbon-rich molecules in different environments. Star nurseries are chemically active before stars mature. Water ice on dust is not Earth water yet. It has not crossed a disk, entered a small body, struck a planet, or survived geological processing. The reservoir is upstream. Beginning does not equal destination. The idea changes habitability thinking. If water ice is common in star-forming material, then water may be available early in many systems. Planetary architecture then decides whether it becomes surface habitability. Supply and outcome separate. Cold chemistry also explains deuterium enrichment. Low-temperature environments can favor heavy hydrogen signatures that later help scientists trace relationships between reservoirs. The Isotope Clue has a birthplace. The physical image stays humble. No shining river runs through the cloud. The beginning may be a frozen video on a grain drifting in blackness. Smallness is part of the drama. Mapping that video across real regions was the missing visual doorway. Once instruments can trace ice signatures in star-forming clouds, the oldest reservoir becomes part of the observable story. SPHEREx gives that doorway scale. Surface area is the hidden trick. Tiny grains collectively provide enormous surface area for atoms to stick, meet, and react. Chemistry that is inefficient in open gas can become effective on dust. Small surfaces make large reservoirs. Ice mantles grow molecule by molecule. The process is not cinematic, but it is consequential. A frozen layer accumulates quietly in cold darkness. The beginning may be slow. Cloud density protects chemistry. In denser regions, shielding from harsh radiation allows fragile molecules and icy mantles to survive longer. Darkness can preserve, collapse later tests that preservation. Material from the cloud does not remain still. Gravity pulls it inward, and each parcel experiences a different temperature and radiation history. The cloud reservoir enters motion. Spectral features are molecular shadows. When background or embedded light passes through icy dust, certain wavelengths are absorbed, revealing what the ice contains. Absence of light becomes evidence. Water is only one ice species. Carbon monoxide, carbon dioxide, methane, ammonia, and organics can join the mantle depending on conditions. The grain is chemically layered. That richness matters for planets beyond water. The same reservoirs that carry ice may also carry prebiotic ingredients or carbon chemistry into disks, though each claim needs its own evidence. Habitability begins as a package, not a slogan. The dust image keeps the story grounded. Instead of vague cosmic mystery, we have a physical surface, a cold temperature, and reactions that can be studied. The invisible becomes concrete. The dust grain picture also explains why water can be widespread. If the chemistry depends on common ingredients and cold surfaces, then many star-forming clouds can host ice mantles under the right conditions. Water becomes part of the galactic raw material, not guaranteed oceans, but available chemistry. The ice mantle is a layered archive. Different molecules can freeze at different times and temperatures, meaning the grain may preserve a sequence of chemical environments. A speck can have strata. Radiation both harms and helps chemistry. Energetic photons and particles can break molecules, but they can also drive reactions that build complexity. A cloud is not chemically asleep. Darkness still has activity. This stage gives the evidence its deepest contrast. The liquid ocean under moonlight and the frozen ice on a dust grain seem unrelated until the chain connects them. The familiar and the invisible meet. The dust grain is easy to miss because it is not grand. Yet, origin stories often depend on humble surfaces. A planet can owe part of its water ancestry to chemistry that happened on objects far too small to see. Scale becomes the surprise. Cloud ice also changes what "before the sun" means. It does not mean a preserved ocean waiting in space. It means molecular ingredients and chemical signatures may have existed in the parent material before the sun formed. The phrase becomes precise. Now we can place the next piece. Cygnus X is a massive star-forming region in the Milky Way, a place where gas, dust, radiation, young stars, and hidden chemistry overlap. To ordinary eyes, much of the story is blocked or blurred. Visible light cannot simply reveal all the cold material inside. SPHEREx looks differently. It surveys the sky in infrared light, where chemical signatures can be separated into many narrow slices. What this changes is the picture of hidden ice as guesswork. The oldest reservoirs can begin to be mapped, even when the ocean link remains indirect. But we need the next constraint. NASA often describes SPHEREx as seeing the sky in 102 infrared colors. That does not mean a rainbow painted for beauty. It means the instrument divides infrared light finely enough to detect patterns that ordinary imaging would miss. Molecules interact with light in characteristic ways. When light passes through or emerges from dusty regions, water ice and other materials can leave identifiable marks, so we keep the scale in view. The Cygnus X result matters because it makes hidden ice feel less abstract. Instead of only saying that cold clouds should contain water ice on dust, scientists can map signatures of that ice across a real star-forming environment. The viewer can picture the evidence moving from theory and small samples into a wider galactic setting. Water ice is not being imagined. It's being traced by the light it absorbs and emits. But the boundary has to stay bright. SPHEREx does not show where Earth's ocean molecules came from. It does not trace water from Cygnus X to our planet. Cygnus X is not being named as Earth's source cloud. The instrument reveals a reservoir type. It shows that interstellar water ice in star-forming regions can be mapped. And that is powerful enough without pretending it is a solved origin label. Think of SPHEREx as opening a door at the back of the story. In the foreground we have Earth's ocean. Behind it, meteorites and comets. Behind them, young disks. Behind those, molecular clouds with ice on dust. SPHEREx helps illuminate that last room. It does not prove which exact path led from that room to Earth. It lets us see that the room is real, chemically rich, and widespread enough to matter. And we can see why that matters. The 102 color idea also helps explain why spectroscopy does more than make a pretty picture. A normal image tells us where light is bright or dark. A spectral map asks what kind of light is missing, shifted, absorbed, or emitted. Water ice has features in infrared wavelengths. So do other materials. By scanning broadly and consistently, SPHEREx can build maps that connect structure with chemistry across large areas of sky. Here's where we slow down. PHAs appear in this environment too. Complex carbon-rich molecules associated with dust and radiation fields. They belong to the chemistry of star-forming regions, but they are not the same as water ice. Treating them separately keeps the science clean. The story is not all interesting molecules equal ocean origin. The story is that water ice, one key reservoir, can be observed in the same broader nursery where stars form. SPHEREx is also valuable because it is a survey instrument. It's designed to map the sky, not only stare at one object. For origin questions, that scale matters. One spectacular target can inspire curiosity, but a map can show patterns. Patterns help scientists compare environments, test models, and ask whether ice reservoirs vary with location, radiation, density, and star formation activity. For Earth's water, the map is an upstream clue. It does not replace meteorites. It does not replace DH. It does not replace disk observations such as V883 Ori. Instead, it adds a visible early reservoir to the chain. We can say, here is water ice before planets. Here is a way to map it. Now the harder question becomes how much of that kind of material survives the journey into planets. That harder question is where many overconfident stories fail. Seeing the reservoir is not the same as proving the route. A cloud can be rich in ice while a future rocky planet still loses most of its water. A disk can inherit chemistry while impacts later erase or mix the record. SPHEREx gives us a gateway, not a finish line, and that is exactly why it belongs in this documentary. The instrument does not make the story smaller by solving it. It makes the story larger by revealing the hidden beginning more clearly. Once we can see interstellar ice reservoirs, the origin of Earth's water becomes a survival problem across environments, not a simple hunt for a single source. SPHEREx reads the sky spectrally. Instead of only making images, it separates infrared light into many colors so chemical signatures can be mapped over large regions. A survey becomes a chemistry atlas. Infrared light is essential here. Cold dust and ice often hide from visible wavelengths, but molecules leave features in the infrared that can reveal their presence. The invisible becomes measurable. Cygnus X gives the map drama without needing hype. It's a real star-forming region, rich with young stellar activity and dusty structure. Water ice signatures there connect the viewer to a living nursery in the Milky Way. The reservoir has a place. The claim must stay upstream. SPHEREx shows the type of environment where early water ice reservoirs exist. It does not identify the birth cloud of Earth's oceans. A doorway is not a destination label. The 102 color phrase needs translation. More colors means narrower spectral bins, and narrower bins help separate overlapping molecular features. The value is precision, not decoration. Pretty pictures are not the point. Mapping PAHs alongside ice enriches the scene. Carbon-rich molecules reveal energetic chemistry in the same regions, but they do not substitute for water evidence. Each signature has its own meaning. Chemical richness is not chemical confusion. SPHERex also helps test variation. Different parts of a cloud may have different radiation fields, densities, and ice abundances. A broad map lets scientists compare those conditions. Patterns matter more than one postcard. SPHERex belongs late in the evidence trail by design. We first need oceans, meteorites, isotopes, disks, and dust so the map lands as evidence in a chain rather than a news hook. Context prevents overclaim. The instrument makes old chemistry current, not because the topic is news-driven, but because new maps let an evergreen question be seen more clearly. A fresh doorway can serve an old mystery. The next question follows naturally. Once we can see the reservoir, we have to ask what fraction of that reservoir can survive the journey into rocky planets. Observation leads to the survival problem. Our map changes the scale of evidence. Single measurements can show possibility. Large surveys can reveal distribution, variation, and context across a region. Scale turns a clue into a map. SPHERex fits the measurement limit theme. It cannot give a genealogy, but it can improve the upstream reservoir map, and that is exactly the kind of partial evidence origin science needs. Partial does not mean weak. Cygnus X is useful because it is active. Star formation, dust, radiation, and molecular material interact there, making it a rich field for tracing ice signatures. The nursery is alive with constraints. Infrared colors separate substances imperfectly but powerfully. Scientists still need models and careful calibration, yet narrow wavelength slices reveal chemical structure hidden from ordinary images. Precision comes from separation. The image should not be treated as a photograph of water. A spectral map is an interpretation of light signatures, not a camera snapshot of blue liquid or white frost. The visual promise needs scientific translation. Our SP4X also connects to organics carefully. PAH signatures show carbon chemistry in star-forming regions, but water origin claims must rest on water-ice evidence. Adjacent chemistry stays adjacent. The mission's value will grow with comparison. As more regions are mapped, scientists can ask whether water-ice reservoirs follow predictable patterns. The first map invites the next map. For Earth, the map is context. It shows that the earliest reservoir required by inheritance stories can be observed in the galaxy. It does not have to live only inside equations. Context is not proof, but it matters. OWN2 SP80RX arrives late because the viewer is now ready for it. Without the earlier chapters, the map could sound like a NASA announcement. With the chain established, it becomes an evidence gateway into the oldest reservoir. Order protects meaning. The instrument's breadth matters for future science. By surveying large areas, SPHEREx can help move from isolated detections toward environmental comparisons. Origin questions improve when patterns replace anecdotes. A map lets science ask better questions. The Cygnus X framing needs geographic caution. It's a star-forming region we can study, not the birthplace of the Sun. The value is analogy and reservoir mapping, not direct ancestry. Place should not be confused with source. The safe wonder is still large. Before planets form, before oceans exist, before shorelines can reflect moonlight, water ice can already be present in the material of stellar nurseries. And that is enough. The SPHEREx chapter should feel like evidence arriving, not hype arriving. The viewer has already learned why early reservoirs matter, so the map lands as a needed observation. It shows a hidden part of the chain becoming measurable. Here is the correct excitement. The mission's boundary is its strength. By saying exactly what SPHEREx does not prove, we make what it does show more trustworthy. Water-ice reservoirs in star-forming regions can be mapped by infrared signatures. Trust makes the map more powerful. Now we can place the next piece. Making water early is not enough. Here is the uncomfortable constraint. A molecule can form on dust before the sun exists, but the path from cloud ice to ocean is brutal. Collapse, heating, radiation, disk chemistry, planet-seismal formation, impact shock, magma oceans, atmospheric escape, and geological recycling all stand between the first ice and the final sea. The question becomes not only where water begins, but what survives. What this changes is the picture of origin as arrival alone. A planet has to keep, store, and return water before the source becomes a sea. But we need the next constraint. Cloud collapse starts the gauntlet. Dense regions fall inward under gravity. Material heats as it gathers. A protostar ignites at the center. Around it, a disk forms from leftovers, still rich with gas and dust. Some inherited ices may be warmed and vaporized. Some molecules may be broken apart. Other material may remain cold enough in outer regions to preserve older ice, or at least older isotope patterns. So we keep the scale in view. Reset is a plain word for a complicated process. Old molecules can be destroyed and remade. Ice can vaporize and later freeze again. Hydrogen and oxygen can exchange between molecules. Ratios can shift. A chemical signature from a molecular cloud may survive in one region and disappear in another. So inheritance is never all or nothing. It's a question of fraction, location, and timing. And we can see why that matters. Disk movement adds more uncertainty. Pebbles drift inward because gas drag robs them of orbital energy. Ice can cross temperature boundaries and release vapor. Vapor can diffuse and freeze again farther out. Larger bodies can scatter. Growing planets can stir material. The disk is not a set of static rings. It's an evolving environment where water can move, change form, and become trapped in different reservoirs. Here's where we slow down. Then planet formation raises the stakes. Planetesimals collide and heat internally. Radioactive decay can warm small bodies enough for ice to melt and alter minerals. Larger impacts can bury water, release it, or drive it away. A growing Earth experiences repeated energetic collisions, including the giant impact associated with the Moon's formation in many models. Every stage can change what water remains accessible. Look at what we have learned. Atmospheric escape matters after delivery. Young stars can be active. Ultraviolet radiation can split water vapor. Lighter hydrogen can escape more readily into space, leaving heavier isotopes enriched behind. A planet's gravity, magnetic environment, atmosphere, and distance from the star all influence retention. Earth kept enough water. Venus and Mars tell us that similar ingredients do not guarantee similar outcomes. Imagine we are following the evidence. Mantle exchange complicates the surface view. Water can be carried downward by subduction once plate tectonics operates. Volcanism can return it to the atmosphere and surface. Minerals deep inside Earth can hold hydrogen. The ocean is not an isolated reservoir sitting above the real planet. It's connected to the interior through long cycles that can blur the record of early sources. Think of the system this way. Late delivery models emphasized the final assembly and addition of water-bearing bodies. Inheritance models emphasize continuity from cloud to disk. Local building block arguments emphasize material near Earth that may have carried hydrogen from the beginning. These become not mutually exclusive in a simple way. They compete over proportions, timing, and evidence strength. The mixed answer is not a compromise for politeness. It's what the filters demand. The key distinction is ancient beginning versus final inventory. Some water chemistry may be older than the Sun. Earth's actual oceans, arranged on a surface after impacts, mantle cycling, escape, and climate evolution, are not ancient cloud ice preserved unchanged. The beginning can be pre-solar, while the ocean as an ocean is a planetary outcome. That distinction protects the wonder from hype. The most beautiful version of the story is not "your glass of water came directly from Cygnus X." The better version is stranger and truer. The chemistry that made ocean worlds possible may begin in darkness before stars. then pass through violent filters until one rocky planet keeps enough to turn blue. Once we accept the survival problem, the evidence pieces fit differently. Meteorites show water-bearing rock. Comets show icy reservoirs with diverse isotope ratios. V883 Ori shows disk inheritance may be real. SPHEREx maps early ice reservoirs. Earth shows retention. None alone gives the whole answer. Together they define the chain. Survival is the hardest filter. A molecule can have an ancient birth and still fail to matter for Earth if it is destroyed, lost, or diluted before the ocean forms. Old does not automatically mean relevant. Collapse heats some material. As a cloud forms a protostar and disk, gravitational energy and radiation change the chemistry. Cold inheritance and hot reset occur side by side. The same system can preserve and erase. Disk drift redistributes water. Icy pebbles migrate, vapor moves, and material can refreeze in new places. A molecule's location in the disk may not be its formation location. The route is not a straight line. Small bodies process their own water. Radioactive decay can warm interiors, melt ice, and create hydrated minerals. The parent body becomes a chemical reactor. Meteorites record processing, not purity. Impacts test every delivery. Incoming bodies can add material while heating the planet enough to lose some volatiles. The retained fraction depends on conditions, speed, angle, and atmosphere. Delivery is filtered at impact. Atmospheric loss keeps reshaping the record. Young stellar radiation can split water and help hydrogen escape. The present ocean ratio may include later planetary evolution. The planet edits the clue. The mantle is a hidden reservoir. Water-related hydrogen can move into minerals deep below the surface and later return through volcanism. Oceans and interior are coupled over time. Surface water has a deep partner. Inheritance survives as a fraction, not a slogan. Some molecules or isotope patterns may pass through, others are reset. Models try to estimate proportions, not declare a perfect lineage. The honest answer is quantitative. Here is where many videos overreach. They jump from ancient interstellar ice to water in a glass. The missing middle is the entire planetary gauntlet. The middle is the science. Holding the gauntlet in view makes the payoff stronger. If any pre-solar chemical ancestry remains relevant after all those filters, the result is more remarkable, not less. Survival gives the story weight. A survival fraction can be small and meaningful. Earth does not need every cloud molecule to survive unchanged for inheritance to matter. Even partial preservation can influence isotope ratios and source material. The question is proportion. Heat creates zones of erasure. Near the protostar or inside impact-heated bodies, old ice may vaporize, react, or lose its original signature. Some paths wipe the slate. Cold creates zones of memory. Outer disk regions, shielded grains, and preserved planetesimals may retain older water or isotope patterns longer. Other paths keep the page. Mixing makes the final ocean composite. Material from different reservoirs can combine until the ocean ratio reflects several histories at once. A blended signal is still a signal. Magma oceans can store water below. Some hydrogen dissolves into molten silicates and later remains in the mantle rather than escaping immediately. Loss and storage compete. Volcanism can rebuild atmospheres. Even after early losses, degassing from the interior can return water vapor and other volatiles to the surface environment. A planet can exhale water later. Impacts vary by angle and speed. A grazing collision, a head-on strike, and a slower accretion event do not retain volatiles the same way. Delivery efficiency is not constant. The survival problem defines the honest title. Earth's water may begin before the sun in one sense, while the ocean begins after planetary filtering in another. Both statements can be true. The survival problem also explains why scientists disagree. Different models give different weights to inheritance, local inventory, and late delivery because each filter is difficult to quantify. Small changes in assumptions can shift the final mixture. Debate lives in the proportions. Survival can mean molecular survival or signature survival. A molecule might be destroyed, while an isotope pattern remains partly inherited through remade water. Those are different claims and should not be merged casually. Continuity has levels. Earth's later geology keeps editing the answer. Subduction, volcanism, weathering, and mantle storage continue long after the initial ocean forms. The planet does not stop processing water once it becomes habitable. The archive remains active. That makes the possible pre-solar ancestry more impressive. Any surviving clue has passed through a chain of events that could have erased it. Ancient chemistry reaching a modern ocean world is not simple, it is hard-won. The gauntlet creates the drama. The survival chapter is the antidote to slogans. Older than the sun sounds beautiful, but without survival fractions and planetary filters, it becomes misleading. The hard middle keeps the phrase scientifically usable. The caution protects the wonder. Every filter also creates possible evidence. Heating, alteration, escape, and storage leave chemical and isotopic traces. The events that obscure the origin also give scientists something to measure. The obstacle becomes part of the record. So what is the best current answer? Earth's water is probably not a single source's story. That may sound less satisfying than naming one culprit, but it is stronger. The evidence points to a chain of reservoirs, carriers, transformations, and losses. Different parts of the chain answer different questions. Confusing those parts is how the story becomes either too simple or too vague. What this changes is the picture of an answer as one label. The useful answer has roles, weights, and stages instead of a single source name. Now we can place the next piece. Asteroid-like material remains central. Carbonaceous chondrites and related bodies provide some of the strongest evidence for water-bearing contributions compatible with Earth's inventory. They contain hydrated minerals and isotope clues that make them hard to ignore. If we ask what kinds of bodies could deliver substantial water-bearing material to a growing Earth, asteroid-like planetesimals remain near the top of the list, but we need the next constraint. Comets keep a smaller but still meaningful role. Their ice makes them visually compelling, and some measured comet families come closer to Earth's water than others. Yet many comet-DH ratios are too different for a simple comet-dominant story. The best answer does not throw comets out. It refuses to let their appearance do more work than the measurements allow. So we keep the scale in view. Inner solar system material complicates the old dry Earth assumption. Enstatite chondrite research suggests Earth-like building blocks may have carried more hydrogen than once expected. If true at scale, some water-related inventory could have been present during Earth's assembly rather than added only afterward. That does not erase delivery, it changes the starting condition. And we can see why that matters. Disk inheritance adds the next layer. Observations such as V883 Ori make it plausible that water chemistry can connect protostars, disks, and comet-like reservoirs. The disk does not have to be a mixing bowl that wipes every older signature clean. In some regions and under some conditions, part of the chemical memory may survive. Here is the bridge that lets the story reach before planets. Here's where we slow down. Interstellar ice supplies the earliest visible reservoir in this chain. Cold dust grains inside molecular clouds can host water ice before a solar system exists. SPHEREx helps map that kind of reservoir in star-forming regions by reading infrared signatures. Again, not as a proof of Earth's exact source, as evidence that the upstream reservoir exists and can now be studied at scale. Look at what we have learned. Earth itself is the final filter. A source can be real and still contribute little if the planet loses the material. A delivery route can be efficient and still be altered by impacts. An inherited molecule can be ancient and still be broken apart before the ocean forms. The planet decides what becomes surface water through mass, heat, atmosphere, geology, and time. Imagine we are following the evidence. The hierarchy matters. Strong evidence supports asteroid-like water-bearing contributions. Comets are constrained and probably not the simple dominant answer. Inner building blocks may have mattered more than older dry models assumed. Disk inheritance is plausible and supported by observations, but not measured molecule by molecule for Earth. Interstellar ice is a real early reservoir, not a direct source label for our oceans. Put together, the answer becomes clear without becoming fake. Earth's oceans are the visible endpoint of a mixed planetary chain. Some ingredients may have been local, some may have been delivered, some chemical ancestry may be older than the Sun. The final ocean formed only after Earth passed that inheritance through heat, collision, escape, burial, and return. Here is why the central question asks where Earth's water begins, not where Earth's water was finally assembled. The beginning may lie in cold interstellar chemistry. The assembly belongs to the young solar system. The survival belongs to Earth. Each stage matters, and each has different evidence. A single source label would be easier to sell. Comets did it. Asteroids did it. SPHEREx solved it. But the universe is not obligated to give us a clean headline. The deeper answer is more useful. Water begins as chemistry, travels as material, arrives through dynamics, and becomes an ocean only if a planet can keep it. The mixed answer is not indecision. It's a ranked synthesis of evidence with different strengths. Some claims are strong, others plausible, and others only speculative. Clarity comes from ranking. Asteroid-like material ranks high. Hydrated minerals, isotope comparisons, and accretion models make carbonaceous bodies serious contributors to Earth's water-bearing inventory. Here is one of the strongest pillars. Comets rank lower as a dominant source. Their ice is obvious, but many DH measurements mismatch Earth. Some families remain possible contributors, especially in limited proportions. The picture is attractive but constrained. Inner material deserves more attention than older models gave it. Hydrogen in enstatite-like building blocks suggests Earth may have had some water-related inventory from early assembly. The planet may not have started empty. Disk inheritance sits in the plausible middle. V883 Ori and related work support continuity across star formation stages, but they do not measure Earth's inventory directly. A bridge is not a census. Interstellar ice is the earliest reservoir, not the final answer. Water can form before stars on dust grains, and SPHEREx can map such reservoirs. The Earth connection remains indirect. Origin depth and source certainty differ. Earth controls the final result. Even a perfect source mixture would be transformed by impacts, escape, mantle cycling, and climate evolution. The planet makes the ocean from ingredients. The cook matters as much as the pantry. The best answer has a sequence: cloud chemistry, disk processing, small body storage, planetary delivery, impact loss, interior cycling, surface stability. Each step changes the inventory. Sequence beats label. The question should feel sharper now. The answer is not, we do not know in a vague way. It's, we know different stages with different confidence. Uncertainty can be mapped. The framing survives the nuance. Where Earth's water begins points to the earliest traceable beginning, while the evidence explains why the final ocean requires later planetary assembly. The promise and the science stay aligned. Mixture does not mean equal shares. One source family may dominate delivery while another contributes isotope heritage and another contributes local hydrogen. The blend has structure. Carbonaceous material carries the delivery weight. Its hydrated minerals make it one of the most concrete lines from small bodies to Earth's inventory. The strongest suspect is rocky and dark. Enstatite-like material shifts the baseline. If Earth's ingredients already contained hydrogen, then later delivery added to an existing reservoir. The planet may have carried seed water. Comets remain a cautionary tale. They look right but often measure wrong for a dominant source. Science corrected the story by trusting ratios over appearances. The obvious answer weakened. Disk inheritance provides depth. It explains how delivery bodies could possess water chemistry older than themselves. The courier inherited the message, interstellar ice marks the oldest visible reservoir in the chain. It shows where water can form before the sun, but not which molecules ended in Earth. Reservoir and ocean history differ. Earth provides the final edit. The planet's mass, impacts, interior, and atmosphere decide what becomes ocean. Origin ends in retention. The best summary is a chain, not a label. Water forms, moves, freezes, reacts, rides, strikes, escapes, hides, and returns. The verbs are the answer. A ranked answer helps avoid mush. We can say asteroid-like delivery is strongly supported, comet dominance is constrained, inner hydrogen is plausible. Disk inheritance is supported but bounded, and interstellar ice is an upstream reservoir. Different confidence levels can coexist. The mixture may vary between planets. Another rocky world in another system could inherit similar cloud ice but lose its water, or receive different delivery bodies and keep more. Earth's path is not universal. Origin is local history applied to cosmic ingredients. The mixed answer also preserves viewer satisfaction. The viewer did not click for nobody knows, they clicked for the real shape of the answer. A chain with ranked evidence delivers that shape. Uncertainty becomes structure. The core sentence is simple enough to remember. Earth's water may begin as pre-solar chemistry, travel through small bodies and disks, and become an ocean only after Earth survives the filters. Here is the documentary in one line. A mixed source can still have a main character. Asteroid-like material may carry much of the delivery case, while inherited ice supplies the deeper ancestry. Different roles do not require equal shares. The answer has roles, not a flat list of ingredients. The mixed answer also explains why the debate lasts. Each evidence stream is strong in its own zone and weaker outside it. Researchers disagree where the zones overlap: amounts, timing, survival, and transformation. The open question is now well defined. Now we need the boundary. Oceans are observed directly. Meteorites can be collected and measured. Comets can be sampled, visited, or studied remotely. Young disks can be observed around other stars. Interstellar ice can be mapped by spectral signatures. Each rung of that ladder is real. Each rung also stops short of the next. What this changes is the picture of uncertainty. The unknown edge is not a fog. It is a boundary we can name. Now we can place the next piece. Earth's ocean tells us the planet ended up water-rich at the surface. It does not tell us the source mixture by itself. Meteorites tell us water-bearing minerals existed in ancient small bodies. They do not perfectly represent all material that built Earth. Comets reveal icy reservoirs with varied chemistry. They do not automatically become oceans. Disk observations show water during planet formation. They do not replay our solar system exactly. But we need the next constraint. SPHEREx maps water ice and related chemistry in star-forming regions. And that is a major doorway into early reservoirs. But a map of interstellar ice is not a genealogical record. It does not put a tracking device on a molecule. It does not tell us which fraction of Earth's ocean, if any, remained chemically continuous from a particular cloud. The evidence is strong in one direction and limited in another. So we keep the scale in view. No instrument watches a water molecule form on a dust grain, enter the solar nebula, freeze into a planet sesamoll, strike Earth, survive a magma ocean, cycle through the mantle, and rise into the sea. That complete movie does not exist. Origin science often works without that kind of movie. It reconstructs history from overlapping clues, each one incomplete alone but meaningful in combination. And we can see why that matters. Not a weakness unique to water, Planetary science often studies events too old, too distant, or too destructive to observe directly. Scientists use samples, isotopes, dynamics, chemistry, crater records, mineral structures, and telescopic signatures. The goal is not perfect memory. The goal is convergence, independent evidence streams pointing toward a limited but durable answer. So future measurements can sharpen the picture. Better interstellar ice maps can show how reservoirs vary across star-forming environments. More disk water measurements can test how often inheritance survives. More primitive samples from asteroids and comets can refine the source families. Better models of hydrogen escape and mantle cycling can show how Earth changed the inventory after it arrived. And comparative planetary science will matter too. Mars, Venus, icy moons, and exoplanets all ask versions of the same question. Water can be present early and still lost. Water can be delivered and still fail to remain on the surface. Water can exist below ground while the surface looks dry. Earth is not only a source problem, it's one outcome among many possible water histories. So SPHEREx should be understood as the beginning of a better map, not the end of the debate. Its value is enormous precisely because it widens the evidence base. It lets scientists see water-ice reservoirs in star-forming regions with new breadth. It helps connect the ocean question to galactic chemistry without pretending the connection is complete. We should leave with a deeper question, but not a blurrier one. The old public story asked whether asteroids or comets brought Earth's water. The better question asks how far back the water-bearing chain can be traced, which stages preserved evidence, and which stages transformed it beyond recognition. And that is clearer because it puts every claim in the right place. Here is the honest boundary. Earth's oceans do not have a single clean label. Asteroids and hydrated planetesimals remain central to the delivery and inventory problem. Comets may have contributed, but probably not as the simple, dominant answer. Earth-forming material may have carried more hydrogen than once assumed. Disk observations make inheritance plausible. Interstellar ice shows where some water chemistry can form before stars and planets. But beyond that, inference begins. Useful inference, evidence-led inference. But inference all the same. The story reaches farther back than the old delivery model alone, yet it does not reach all the way to certainty. That tension is the shape of the answer. Now the evidence ladder begins with direct reality. Earth has oceans. We can observe them directly. Everything older than the present ocean must be reconstructed through samples, signals, and models. The certainty decreases as we move backward, but meteorites provide physical samples. They let scientists measure minerals and isotopes directly, but they are fragments from selected parent bodies, not a complete inventory of early Earth. A sample is powerful and partial, and comets provide remote and occasional direct clues. Spacecraft and telescopes can measure gases and isotopes, yet the comet population is diverse and incompletely sampled. One comet never stands for all comets. So disk observations provide analogues. Young systems let us watch processes related to planet formation, but they are not our own early solar system replayed on demand. Analogy needs boundaries, and interstellar ice maps provide upstream context. Spectral signatures show reservoirs before planets, but they do not trace the full history of Earth's water molecules. A reservoir is not a root. Now models connect the rungs. Dynamical simulations, isotope models, chemical networks, and atmospheric escape calculations test whether the pieces can fit. The bridge is mathematical as well as observational, and future samples could change the weights. More primitive asteroid and comet material may strengthen or weaken source families. Better laboratory work can refine hydrogen and oxygen constraints. The answer will become ranked more sharply. So future maps could change the upstream picture. SPHEREx and other observatories may reveal how common or variable water-ice reservoirs are across star-forming regions. The oldest reservoirs may become easier to compare. The stopping point is not failure. Knowing where evidence ends prevents the story from becoming hype. It also shows exactly what the next generation of observations must solve. Limits are useful. The final boundary is simple. Earth's water story can honestly be traced back into pre-planetary reservoirs, but not as a single proven molecular journey from one cloud to one ocean. Here is the line to hold. A confident answer needs categories: observed, sampled, measured remotely, inferred, modeled, and speculative claims should not be mixed as if they carry the same weight. Categories protect trust. Observed oceans sit at the top. We know Earth is water-rich now. The challenge is reconstructing how that state emerged. The present is clear, the past is layered. Samples give the strongest ancient constraints. Meteorites and returned materials let laboratories measure chemistry directly, though never completely. Touching evidence still has context. Remote disks widen the timeline. They reveal processes before planets finish, but each system has its own history. Comparison needs many examples. Spectral cloud maps widen the beginning. They show early reservoirs, not final outcomes. That distinction is the whole guardrail. The map starts the chain. No single future mission will solve every link. Progress will come from combining maps, samples, models, and planetary comparisons. The answer will tighten by convergence. The safe conclusion is still strong. Earth's water story reaches beyond simple asteroid versus comet delivery into older reservoirs and inheritance questions, and that is already a deeper result. The unsafe conclusion remains banned. SPHEREx did not solve Earth's oceans, and no Cygnus X molecule has been traced into our sea. The doorway stays a doorway. Now we can hold Earth water in a clearer form. The ocean is not explained by one delivery event. It's explained by survival through formation. We need sources. We need timing. We need chemistry that remains readable after violence. So the question is not only where the water came from, it's how enough of it stayed connected to Earth long enough to become the planet we know. And that is where the answer has to stay honest. What this changes is the picture of a satisfying ending. The answer can be limited and still be stronger than the old simple story. But the evidence stop is also the ethical stop. A science channel earns trust by refusing the stronger claim when the evidence does not support it. That restraint is not caution for its own sake, it is accuracy. The line matters, and SPHEREx makes one part of the ladder stronger. The interstellar reservoir can now be mapped with new breadth, giving the earliest stage more observational weight than before. The old reservoir becomes less abstract, so the missing link remains genealogy. We still cannot follow individual water molecules through every stage from cloud to ocean. Models can connect plausible pathways, but observation has limits. The invisible route stays partly inferred, so the final answer is bounded but meaningful. Earth's ocean story reaches back beyond the familiar asteroid and comet delivery debate into disks and interstellar ice, while the exact source mixture remains unresolved. That boundary is the honest payoff. Now a good ending should leave us more certain about the uncertainty. Not vague, not disappointed, but oriented. We know the chain, the strongest clues, and the places where inference begins. And that is real satisfaction, and the boundary also sets up the future. More SPHEREx maps, more disk measurements, and more primitive samples will not replace the story. They will tighten the links between its stages. The trail is not finished, but it is visible. Here is one more boundary. The phrase, "where water begins," can mean several things, and a careful answer has to separate them. Water as a molecule can form in cold chemistry. Water as a planetary ingredient can enter a disk or small body. Water as an ocean begins only when a planet has a surface and atmosphere able to hold it. These stages are connected, but they are not interchangeable. That separation is why the evidence trail can feel both longer and stricter at the same time. Longer because it reaches beyond asteroids and comets into disks and molecular clouds. Stricter because every step must be named honestly. A cold cloud supplies an early reservoir. A disk processes and distributes material. Small bodies store and deliver it. Earth filters the result. Each verb limits the claim. If future SPHEREx maps show water ice is widespread across many star-forming regions, the case for early water availability grows stronger. If future disk observations show inheritance signatures in many young systems, the bridge from cloud to planet-forming material grows stronger. If future samples refine meteorite and comet ratios, the delivery mixture becomes clearer. None of those advances needs to pretend that one telescope solved everything. The strongest future answer will probably be less like a headline and more like a budget. How much came with local building blocks? How much arrived through carbonaceous material? How much from comet-like bodies? How much isotope memory survived from the cloud? How much did Earth lose and later return from its interior? The numbers may shift, but the structure of the question is now visible. That structure is the real satisfaction. We can stop asking for one clean origin label and start asking where each part of the chain is strongest. The meteorite evidence is strongest for small body water-bearing material. The comet evidence is strongest for diversity and limits. The disk evidence is strongest for inheritance being plausible. The interstellar ice evidence is strongest for the early reservoir. Earth evidence is strongest for survival and transformation. So when a future article says water is older than the sun, the careful listener will know what to ask. Older in what sense? Molecules, hydrogen inventory, isotope signature, reservoir ancestry, final ocean. The phrase can be true in one sense and misleading in another, not pedantry. Here is the difference between a documentary answer and a slogan. And when a future image shows ice inside a star-forming cloud, the careful listener will know how to place it. Not at the end of the story, not as a direct photograph of our ocean's birthplace, at the beginning of the traceable chain where chemistry becomes available to the systems that may one day make planets. The evidence stops before certainty, but it does not stop before meaning. It lets us say that Earth's water story is deeper than late delivery alone. It lets us say asteroids and hydrated planetesimals are essential but not ultimate. It lets us say interstellar ice belongs in the ancestry without turning ancestry into proof of final source. Here is the line the evidence has been walking from the first wave at night to the last cold grain of dust. The ocean is familiar because we live beside it. The origin is strange because the path behind it crosses environments no human could survive or see directly. Science connects those environments with patient constraints. At the edge of the evidence, the story does not collapse. It becomes sharper. We know what is observed. We know what is sampled. We know what is mapped. We know what is inferred. And we know which tempting claims must wait for better proof. Now we can hold Earth water in a clearer form. The ocean is not explained by one delivery event. It's explained by survival through formation. We need sources. We need timing. We need chemistry that remains readable after violence. So the question is not only where the water came from, it's how enough of it stayed connected to Earth long enough to become the planet we know. Hold two images together. The first is a dark ocean under the moon, heavy with motion and weather and life. The second is a grain of dust inside a cloud, so small it almost disappears from imagination, carrying ice in silence before a star has formed. Between them sits the whole chain: collapse, disk, snow line, planetesimal, impact, magma, atmosphere, mantle, rain, and sea. No single image owns the answer. The ocean shows the result. The dust shows the possible beginning. Meteorites show delivery and storage. Isotopes show memory and alteration. Young stars show inheritance may pass between stages. SPHEREx shows that hidden ice reservoirs can now be mapped, not only described. The honest story is more beautiful than the simple one. A simple answer would make water a package delivered to Earth. The evidence makes it a history. A history can have chapters, reversals, missing pages, and surviving clues. Earth's oceans are not less wonderful because the answer is mixed. They are more wonderful because the mixture held together long enough to become a world. The final restraint is simple. We should not shrink the story to whatever is easiest to title. Asteroids matter. Comets matter. Inner building blocks matter. Young disks matter. Interstellar ice matters. Earth matters most of all, because Earth is where the inventory became an ocean. The strongest version does not choose one and erase the rest. It asks what role each one can honestly play. Here is the difference between mystery and confusion. Confusion throws evidence together until nothing is clear. Mystery arranges the evidence so the unknown edge becomes visible. Earth's water still has that edge. We can see it now more clearly than before, and SPHEREx helps illuminate one of its oldest rooms. But the door it opens leads into further work, not a final label. So the honest answer is not smaller than the headline, it's larger. Earth's water begins wherever the traceable chain first becomes real, in cold chemistry, in disk inheritance, in water-bearing rock, and finally in a planet capable of keeping the result. The ocean is not one event, it's the successful end of many earlier events. So where does Earth's water begin? Not in one place we can label perfectly. The ocean begins as an ocean on Earth. It becomes stable only after a rocky planet survives heat, impacts, atmosphere loss, mantle exchange, and time. No molecular cloud makes a shoreline. No asteroid delivers a finished sea. But the water story begins earlier than the shoreline. Asteroids and hydrated planetesimals remain central because they offer a strong route for water-bearing material to reach Earth. Comets remain part of the wider story, but their isotope ratios make the old simple comet answer too weak. Earth-like building blocks may have carried more hydrogen than older, dry inner solar system models allowed. Young disks show that water chemistry can move through planet formation stages. Cold molecular clouds show where water ice can form on dust before stars are born. And SPHEREx gives us a new way to see part of that earliest reservoir. Not the source label for Earth, not proof that our oceans came from Cygnus X, a doorway into the hidden ice that exists before planets. Here is the real payoff. Earth's water is a delivery story, but it is also a survival story. It's a chain. Chemistry begins in cold places. The next natural question is what a young planet must preserve before water becomes an ocean instead of a passing ingredient.